Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tam from Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the benefit of BSc Physical Sciences students. In this paper on Basic Physics 2, we are passing through the section on radioactivity, especially natural radioactivity. We saw in the previous lectures about the nature of the radiations coming during decay process. We will see in this lecture decay series, half-life period, the effects of radiation on life, and some problems or exercises. Let me show you the natural decay series uranium-238. Uranium-238 after 4.5 billion years gets transformed into thorium, then protoactinium, then uranium-234, then this uranium-234 goes to uranium-230 after so many thousands of years, then this thorium after alpha decay goes to radium. What I would like to tell you is it takes a very long time, and the point is this goes on until you reach a stable state. The stable state that you have got here, uranium again it is radioactive, it goes to thorium, protoactinium and all, actinium, francium and thorium, it goes to radium, radon, and in general most of them go to a stable state, namely lead will be the final thing where it becomes very stable. And with regard to thorium-232, you have here it goes to polonium, from polonium to lead, lead to bismuth, bismuth to polonium-212, and then it goes to lead. Finally, the important thing is lead is stable. So, most of the radioactive elements after lot of decay processes, emission of alpha particles, beta and so on, finally comes to a stable lead. That is what I wanted to tell. We will now move on to the radioactive series which I have been talking to you. For example, the principal isotope of uranium-238 that constitutes 99.3% of natural element has a half-life of 4.5 into 10 to the power of 9 years. Half-life is nothing but the time taken for 1 gram which is radioactive, half of it becomes non-radioactive after a period of 4.5, whatever be the thing. After so many years, half of it will become radioactive, half of it will become non-radioactive. If 1 gram, then only half a gram will be radioactive. Then the radioactive series which we have been discussing, any of 4 independent sets of unstable heavy atomic nuclei that decay through a sequence of alpha beta decays that I showed just now until a stable nucleus. What is a stable nucleus? That is lead is achieved. These 4 chains of consecutive parent and daughter nuclei begin and end among elements with atomic numbers higher than 81 or 83, which is the atomic weight of thallium. 81 is the atomic weight of thallium, 83 is the atomic number of bismuth. As you know, the members of each set are genetically related by alpha and beta decay. These 3 sets which I will be discussing initially, the thorium series, uranium series and actinium series, called natural or classical series, are headed by naturally occurring species of unstable nuclei that have half lives comparable to the age of the elements. By 1935, these 3 radioactive series have been fully delineated. The 4th set, the so called Neptunium series, is headed by Neptunium 237, which is a half life of several thousands of years. That means, the radioactivity contained in Neptunium will never die, it will extend for a very long period. Its members are produced artificially by nuclear reactions and do not occur naturally. All their half lives are short compared with the age of the elements. Because of the 2 pertinent decay processes which result either in no change or in a change of 4 units in the mass number. The mass numbers of all the members of each series are divisible by 4. That means, alpha particle emission with a constant remainder. Within each series, the mass number of the members may be expressed as 4 times an appropriate number integer, you got 4n here, plus a constant for that series. Thus, the thorium series is called 4n series. So, thorium giving rise to alpha, beta and all these things coming to a very stable nucleus, that is called a 4n series. You have the radioactive decay, right, it comes to a stable state. The Neptunium series is called a 4n plus 1 series. Then the uranium series is called the 4n plus 2 series. The actinium series is called the 4n plus 3 series. The thorium series begins with thorium 232 and ends with the stable nuclide lead. As I told you, thorium ends with lead, which is very stable. It starts with mass number 232, ends with a stable lead whose mass number is 208. The Neptunium series ends with bismuth, okay, that is very important. The Neptunium series, named after for its longest lived number, Neptunium 237, it ends with bismuth 209. The uranium series begins with uranium 238 and ends with lead. The actinium series, named for its discovered member actinium 227, begins with uranium 235 and ends with lead 207. Alpha decay involves the ejection from an unstable nucleus of a particle composed of 2 protons and 2 neutrons, as all of you know. Thus, alpha emission lowers the mass number by 4, that is well known by now. At the head of the thorium series, for example, thorium 232 undergoes alpha decay to uranium to radium 228. Negative beta decay, symbolized by a smaller arrow, involves ejection from an unstable nucleus of an electron and an antineutrino that are produced by the decay of a neutron into a proton. The process lowers the neutron number by 1 unit, raises the atomic number by 1 unit and leaves the mass number unchanged. I told you that mass number the charge and the energy, everything ought to be conserved. At the end of the Neptunium series, for example, lead 209 undergoes negative beta decay to bismuth 209. Branching, that is the decay of a given species in more than one way, occurs in all 4 of the radioactive series. We talked about uranium series, thorium series, neptunium series and all. So, in all the 4 series, branching is possible. For example, in the actinium series, bismuth 211 decays partially by negative beta emission to polonium 211 and partially by alpha emission to thallium 207. Uranium, radium, thorium occur in 3 natural decay series headed by uranium 238, thorium 232 and uranium 235 respectively. In nature, radionuclides in these 3 series are approximately same, in which the activities of all radionuclides within each series are nearly equal. 2 conditions are necessary for secular equilibrium. The first, the parent radionuclide must have a half-life much longer than that of other radionuclide in the series. Second, a sufficiently long period of time must have elapsed. 10 half-lives of the decay product having the longest half-life to allow for ingrowth of the decay products. Under secular equilibrium, by secular equilibrium what we mean is the half-life of the parent nucleus should be much higher compared to the daughter nucleus. The activity of the parent radionuclide undergoes no appreciable change during many half-lives of the decay products. Radioactive decay occurs when an unstable or radioactive isotope transforms to a more stable isotope, generally by emitting a subatomic particle such as an alpha or beta particle. Gamma radiation is not a mode of radioactive decay. Whenever there is a radioactive decay, we have been seeing radioactive decay series, gamma is not involved, unlike that of alpha and beta. Radionuclides that give rise to alpha and beta particles are those that emit significant gamma radiation. Rather, it is a mechanism by which excess energy is emitted from certain radionuclides. The nuclear energy levels, the gamma radiation, the excited nucleus going to a lower energy nucleus, there will be emission of gamma radiation. As I told you in the previous lecture also, the gamma emission comes because of the fact that the nucleus comes from excited energy level to a lower energy level. As in the case of optical spectroscopy, you have got the nucleus coming from a higher energy state to lower energy state. Because of the energy difference, the gamma radiation is coming, it is a photon. Second thing is during the decay processes, the neptunium series or actinium series, you have got emission of alpha and beta particles, but not the gamma. The radiation dose associated with gamma may pose a health concern. Gamma is injurious, but of course, the same gamma is used for curing cancer. For simplicity, only significant gamma emissions associated with major decay modes are considered. Radionuclides listed are those for which radiation dose associated with gamma rays may pose a health concern. The first is generally met for the uranium 238, thorium 232 and uranium 235 decay series in naturally occurring ores, while the second condition may not be met for all ores or other deposits of uranium and thorium. It is reasonable to assume secular equilibrium. By secular equilibrium, what I told you earlier was that the half life period of the parent nucleus will be much longer compared to that of the daughter nucleus. It is reasonable to assume secular equilibrium for naturally occurring ores to estimate the concentrations of various daughter radionuclides that accompany the parent. The state of secular equilibrium in natural uranium and thorium ores is significantly altered when they are processed to extract specific radionuclides. After processing radionuclides with half life less than 1 year will establish equilibrium conditions with their longer lived parent radionuclides within several years. Long decay series, for example, the series for uranium 238 may be present as several smaller decay series headed by longer lived decay products of the original series, that is headed by uranium 238, uranium 234, thorium 230, radium 226, lead 210 in the case of uranium 238. Each of these subseries can be considered to represent a new separate decay series. Understanding the physical and chemical processes associated with materials containing uranium, thorium and radium is important when addressing associated radiological risks. We have not discussed the radiological risks or the effect of the gamma radiation in particular on human beings and elements, which should be taken up at a later stage. The radiological risks are to be discussed in detail in the decay modes considered for uranium, radium and thorium. The contributions of radionuclides having half lives less than 1 year were included in the risk coefficients. In some situations, it will be necessary to add the radiological risk identified for a given radionuclide to that of its parent radionuclide to properly represent the total risk. For example, radiological risk for thorium 232 is comprised of the risk for thorium 232 plus the risk for rhodium 228. Now, let us think of some of the nuclear reactions. You see here in the diagram a parent nucleus here. The parent gives rise to alpha particle and then you get a daughter. So, a nuclide is a specific atom with a given number of protons and neutrons. We use the term parent daughter nucleides to describe a parent nuclide decaying to produce a daughter nuclide. So, a parent nucleus will decay means give rise to alpha particle, the alpha decay, and then because the alpha particle has come out, the mass number has been reduced by 4, there remains what is called a daughter with a mass number reduced by 4 compared to the parent nucleus. Balancing nuclear equations. Difference from general chemical equation is in that mass numbers, protons plus neutrons and atomic numbers are balanced, not the elements or atoms present as. You see, the chemical reactions and the nuclear reactions are very different. In chemical reactions, the particles which are participating are the electrons in the chemical reactions. Nuclear force is a very strong force compared to the electrostatic forces. Therefore, in nuclear reactions what is important is what is happening inside the nucleus. There are the nuclear reactions, and the nuclear reactions are different from the chemical reactions. Again, I will go to the example of the parent uranium 238-92 here give rise to alpha particle plus daughter thorium 234-90, where the mass numbers are equal to 238, right, 234 plus 4, the atomic numbers are equal to 92. So, the nuclear reactions are different from the chemical reactions. Now, we will have some exercises as carry home problems to be done by the students. Complete the following nuclear equations by identifying the unknown. 28 oxygen, 20 the mass number of oxygen, going to 20 fluorine, 9 is here at the bottom. What is 9? 9 is the atomic number. You see 8 on the left hand side, then it becomes 9 on the right hand side. The atomic number has increased. Therefore, what should happen to the region left out? That should be -1 should come here. Similarly, you have the magnesium going to phosphorus and then the alpha particle. Similarly, beryllium plus alpha particle going to carbon, and what are the things to be inserted in the left out region should be done. The exercise 2 that you have here, write the complete nuclear equations for the following processes. From the lectures we have seen so far, iron 59 decays by beta emission. You should know what should be from iron 59, what is the daughter nucleus and what should be the associated particle, that is beta emission. Radium 226 decays by alpha emission, write down the equation. Manganese 50 decays by positron emission. Now, for that also you have to write down the equation. Cesium 118, the mass number is 118, is produced when a radionuclide decays by beta emission, that is the electron being emitted during this process. What is, write down the nuclear equation, that is the exercise 2. Now, we will pass on to some of the other things which we have not discussed in a great detail. I told you about the half life. By half life, what we mean is you take 1 gram of a material which is radioactive. In 1 hour, suppose the half life period is 1 hour, that means in 1 hour 50% will become non-radioactive, only 50% will be radioactive. Out of 1 gram, 50% means half a gram will be radioactive. The half life period is 1 hour. The second hour, out of half a gram, quarter gram is radioactive. In the third hour, from quarter, half of quarter, 1/8 of the material will be radioactive. This is so called half life period, and you have what is called the decay curve is the one to be drawn, and half life period is an important concept that should be understood with regard to the nuclear decay processes. Apart from that, I was mentioning about the health risk, the risk coefficients and so on. The gamma radiation has got a higher penetrating power. Therefore, as I told you that it can penetrate even the steel bar, it is a health hazard, but at the same time the gamma radiation or the gamma camera is used in cancer hospitals to cure or to eliminate the cancer cells. Not only gamma, you talk of cobalt therapy. You have heard of I do not know whether you heard of cobalt therapy. gamma camera. So, the gamma radiations coming from cobalt, cesium and other radioactive sources, they are called the radioisotopes. They are called radioisotopes for a simple reason they are emitting or capable of emitting gamma radiation. These gamma radiations can be used to cure cancer. Not only curing cancer, there are other biological applications of gamma radiation. So, in the time to come these things are to be covered. Now, let me pass on to the summary of the session. One of the conditions to be satisfied for equilibrium is that the parent radionuclide must have a half life much longer than that of any other radionuclide in the series. The term parent daughter nucleides to describe a parent nucleide decaying to produce a daughter nucleide. The amount of time required for the radioactivity of a radioactive sample to decrease by half is called the half life period. A specific atom with a given number of protons and neutrons is called a nuclide. The important radioactive series are uranium 238, uranium 234, thorium 230, radium 226 and lead 210. With this, we will now pass on to the question session. The questions to be asked are: what is the difference between chemical reaction and nuclear reaction? What is the decay mode of radium 226? What is the instrument which is used to measure the radioactive decay? Fill up the missing box. Lead undergoes a radioactive decay. You got a mass 214, 214 here, 82 here, 83 here, fill up the box here, lead going to bismuth. With this we come to the end of this lecture. The rest of the things we will see in the lectures to come. Thank you.